All right, so if you wouldn't mind having a look at the screen. So what I'm going to do is I'm just going to take a complex number like 1, okay? So 1 plus 0y, that's exactly the same number as we're dealing with on the screen here, or on the board here. Now, what I'm going to do is I'm going to raise this to different powers, and I'm going to show you where you find the solutions. So at the moment, I'm just taking the first root of that complex number, right? So I'm not really doing anything fancy. So therefore, if I just take the first root of 1, that's just going to be equal to 1. Hence, I've just got that arrow across there. Okay, but watch what happens if I'm trying to solve equations of different orders. So at the moment, by the way, I've just substituted w for x here. That's all that's going on the screen. Okay, so if I try then a different power, so if I try w squared instead, okay, so I take the square root, can you see that your positive 1 and your negative 1 appears as you expected? Yeah? So your positive 1 and negative 1, that's what you told me. Yeah. And you can see that on the screen. Now watch what happens if I try and take the cube root of 1, which is obviously, we found 1, so you're expecting 1 on there, but let's see where the other two solutions are. Okay, so there you go. So can you see the other two solutions? The reason why you couldn't tell me them is because they're complex, yeah? And they don't look particularly nice complex numbers either, right? They look sort of, yeah. Equally, if I try the next one, which you told me was x to the power 4 equals 1, gave me 1, negative 1. I'm expecting 4 solutions, there's 2 more. Anybody want to hazard a guess, given what I've just drawn on the screen, where the other 2 solutions are?
They'd be on the y-axis.
Or imaginary axis, yeah? So what do you reckon they're going to be?
Just 1 I and minus I.
Perfect. Let's give it a go. Let's check it out. Yeah, there you go. So I and negative I. So do you notice, in fact, if I just keep trying raising it to different powers, do you notice that all I'm doing here is I'm just figuring out exactly where the roots are? But crucially, all of the roots are equally spaced. Look at the screen.
Yeah.
You see that? Okay. So if I just stop it at some really big number, like for example 10, let's say. Okay. Can you see that I have 10 roots, so 10 sort of arrows across there, 10 roots, but they're all equally spaced. Okay, so that's kind of a really important observation, so I'll write it down on the screen. Okay, so when we take roots of any number, first of all, if we take, for example, the nth root of a number, okay, we are expecting n roots. Make sense? So that's the first thing we said, right up here, n roots. Also, as we've just observed, those roots have to be equally spaced. Okay, so those are the 2 things I want you to observe. If you want to take the nth root of a complex number, or expect any number, okay, because this of course is the nth root of 1, you're expecting n roots, and those roots have to be equally spaced. So in fact, we can think about the spacing of these roots. Because are you happy that a full turn is going to be 2 pi? Right, 360 degrees, 2 pi. If I've got n roots which are equally spaced, the spacing between the roots,
Divided by,
perfect. Yeah? So in other words, I can tell you right now, the spacing between all of those roots is going to be 2 pi divided by 10 or pi divided by 5, the ones on the screen. Yeah? So that's an important observation. Okay. Now clearly I was just working with 1, okay, here. So if I combine this with de Moivre's theorem, which remember was raising it to different powers, if I take a number which isn't 1, okay, take another number, it should also be that the argument, or the modulus rather, should decrease or increase, okay, because I'm obviously going to be raising it to different powers, right? Let me show you. So if I take this back to 1 again, and if I take a number like 1 plus I like 1 plus I because it's a nice roundish number in complex terms. So if I keep raising it to different powers, watch what happens. So I still get those roots, but can you see that every time I take a new root, in fact let me draw some circles on here as well, can you see every single time I take a new root, I get smaller? Yeah? And the reason being is because I'm literally taking that modulus, think about de Moivre's theorem, I'm taking that modulus and I'm raising it to different powers. Now in this case the power is going to be a fraction, hence the reason why the modulus is getting smaller. Yeah, so the bigger the fraction, the smaller the modulus every single time of my root. Does that make sense? We'll see an example in a second. I want to take a break first of all. But basically, you get this pretty pattern which appears, and obviously you can do all sorts of fancy things like, you know, moving it around and getting fun stuff going on there. Okay. But does that make sense in principle? Okay.
Yeah. I just didn't understand why it becomes smaller.
Because it's getting smaller. Okay. Just think about Moivre's theorem. Okay. So if you take z to any power, of course it could be a fraction. Okay. So actually, I'm going to raise it to a fractional power. Okay. So if I take this as 1 over n, because of course this is the same as root of n, do you see? Then in other words, my r is going to be raised to 1 over n, hence it's going to be getting smaller, all right? And then obviously cosine of, in fact I'll just write it as Euler form because it's quicker. 1 over n times theta, lots of I. That's basically it. All right, okay, let's take a 10-minute break and yeah, we'll finish this off.